Hi, I'm Felix Hennings. I'm researcher at the TU Berlin and work in cooperation with the Zuse Institute on the problem of operating gas networks. In this video, I will give a short introduction to the topic and give some general advice on how to approach big industry projects. Let's get started. To get an idea on what the problem is about, imagine a gas network operator controlling the network and facing a critical network situation. Solving the given problem is like being a navigation system for the operator that gives advices on how to operate the network in the future and overcome these critical situations. You can imagine this like being similar to a navigation system for cars that finds an optimized route to reach your target destination. In technical terms, you can summarize the problem as optimization of short-term transient gas network control of large real-world networks. Short-term transient here means that you consider the control problem over time and take the next 12 to 24 hours into consideration. To solve the problem, we are given the topology of the network, so the position of all the single elements and their connection to each other. Then we are given the initial state, so the current modes of the single elements and the distribution of the gas in the network. And for the future, we are given the demand and supply forecasts on what we expect to happen at the boundary nodes. So how much gas will be entered, how much gas will leave the network. Having this, the goal is to find a control for each of the network elements such that the network overall is operated best. Here, a good control means that we fulfill the demands given for the future while changing the single elements in the network as little as possible, so keeping the network as stable as possible over time. So, what elements can be found in the gas network and how do we actually operate the network with them? First, we note that we represent the network as a directed graph where the single elements are represented by the arcs of the network and the nodes denote the junctions between these elements. The main part of the network consists of pipelines, which are purely passive elements which have volume attached. The main quantities to describe gas flow in a network are the pressure on the nodes and the mass flow over the arcs. Especially the pressure is important here because the gas flow follows the pressure, so it goes from high pressure to low pressure. Another important quantity is that gas is compressible, so when you have a pipeline and some gas enters the pipe on the one side but does not leave on the other side, this is totally feasible, and just the amount of gas in the pipe increases and thereby also the pressure in the pipeline. Therefore, you can think of the network as being big storage by itself. In addition to the pipes, we have some active elements in the network which we can actually control. First, there's a valve, which has two different states, the open and the closed state, and by opening or closing a valve, we can connect or disconnect the network at this element. Then we have the compressor element, which can increase the pressure in the direction of the flow, and as a counterpart, we have the regulator, which decreases the pressure in the direction of the flow. Finally, the time for the future is split into individual discrete time points and is therefore not continuous. With this knowledge, we can now have a look at some basic example for transient gas network control. Here we see an artificial toy example of a gas network. You can recognize all of the single elements from the last slide, denoted by their corresponding symbols. In the picture, you see in the middle the compressor, then we have two control valves, one at the top of the compressor and one at the bottom of the compressor, and then on the very bottom, left to right line, there's one valve. In addition, there are a lot of pipes between the elements, similar to a real-world network. Before and after each of the elements, we have a single node. The inner nodes of the network are represented by small square symbols, and for the boundary nodes where the gas leaves or enters the network, we have the triangle symbols. The two triangles pointing to the top are the entry nodes, and the triangles pointing downwards, which we are given 4 in this example, are the exit nodes. In addition to the topology, we also see the current state of the single elements in the network. We displayed the two quantities we previously talked about, the pressure and the flow. The pressure is visualized by color, where red stands for a higher pressure and blue stands for lower pressure, as you can see from the two identical axes on the right-hand side. The pressure color is given for each of the nodes, and also the arcs inherit the color of their incident nodes, if there's flow over the arc. The amount of flow going over an arc is depicted by the size of the arc. The thicker the arc, the more flow is going over it. In addition, you can see the flow direction, which is illustrated by the small white triangle symbols on each of the arcs. There are also black arcs. This means that this arc has zero flow and there's nothing currently happening there. Finally, you can also see the current state for each of the active elements. There are two different colors displaying the current mode. If the element is closed, then it has a red color. That means there's no flow going over the element and the pressure at its two nodes is completely independent of each other. For an active element with non-zero flow, the color of the element would be blue. Remember that valves have the same pressure level at both sides of the element in case they are active. Compressors increase the pressure, so the pressure in front of the element is lower than the pressure after the element, and regulators decrease the pressure in flow direction, so the relation here is the direct opposite. From the initial state displayed for this network, we see that there is flow on the lower pipeline going from the left to the right through the open or active valve. In the top area, the three remaining active elements are all closed and no flow is happening here. The pipeline going from the bottom to the top has an equal pressure level of 50 bar, while the pressure in the top right area is only 25 bar. This top right area is the low-level pressure area of this example network, since here we are only allowed to have at most 30 bar. Keep this in mind for the scenario we see in a moment. Together with this initial state of the network, we are given a future scenario for the flow values. In this scenario, the bottom flow from left to right will be shut down completely. It will be replaced by an inflow entering the network at the bottom right and an outflow at the top of the network. A little later, some outflow from the top node will be reassigned to the exit in the low-level pressure area. The last important thing to know about this example is the fact that the top exit can only withdraw gas at a minimum pressure level of 55 bar, so the network control will have to ensure that this requirement is fulfilled. When we start our animation now, we will see the network state evolving over time. The control of the sync elements is optimized to fulfill the demands while changing as little as possible. Let's start our animation and see what the solution looks like for this scenario. We will see that the bottom valve will already close before the flow at the bottom is completely shut down. We do this since the pressure in the bottom right and the top area have to be equalized, and the still withdrawing exit can do the job for us. Furthermore, we see that now the compressor station has been turned on, since the top exit is withdrawing gas and we have to fulfill the minimum pressure requirement. At last, we will also turn on the remaining control valve to regulate the gas flow into the low-level pressure area, since the exit in this area will start withdrawing gas now as well. That was our small example on gas network control. If you like, you can skip back in the video and rewatch the animation a few times to really see and understand the interaction between the modes of the active elements and the physical quantities in each of the different areas of the network. After this demonstration of a basic gas network operation example, we want to take a closer look now at the single elements and their corresponding models. We start with the pipes. Gas flow in pipes can be described by the Euler equations. These are a set of differential equations that assume a straight pipeline and model the flow in one dimension only. We therefore neglect part of the turbulences here that would have to be modeled when we assume a three-dimensional flow in a pipeline. These Euler equations are typically transformed and further simplified to be tractable in an optimization setting. The version that we displayed is called the friction-dominated variant, where the variables denoting the pressure with P and the mass flow with Q are highlighted in red. Among some other things, we assume for this variant a constant temperature of the gas, which is a reasonable assumption for underground transport pipelines. Despite the simplifications, these equations are still hard to solve. The reason for this is a nonlinear and non-convex term describing the pressure loss in the pipe due to friction. On the lower right, we plotted the relationship between flow, pressure level, and pressure loss for an example pipeline. The next elements we want to look at are the valve and the regulator. The valve does not have any constraints in addition to the already described behavior for its two discrete states. If it is open, it connects its end nodes so the pressure has to be equal on both sides, and the flow over the valve is not limited. If the valve is closed, the end nodes are disconnected. Therefore, we do not have a restriction for the pressure, but the flow has to be zero. The regulator reduces the pressure by changing its opening degree, which can be remotely controlled. Therefore, it has an additional discrete state in comparison to the valve, in which the pressure is reduced and the flow can only be positive. Backflow against the orientation of the element is not possible in this mode, since usually the internal control unit of the regulator is programmed to automatically close the element in this case. We continue with the compressors. Let's start with the description of a single compressor unit. A compressor unit represents the combination of a single compressor, which is the actual machine performing the compression of the gas, and a corresponding drive to deliver the power necessary for the compression. In the diagram we displayed in gray a typical feasible operating range of a compressor unit in terms of compression ratio and the volumetric flow rate. The colored lines represent additional restrictions based on the pressure level of the gas going into the compressor. Those lines that are red denote the restriction imposed by the maximum power that the drive is able to deliver. This maximum power value, together with a given non-convex function describing the power needed for compressing at a single specific point of operation of ingoing pressure, outgoing pressure, and mass flow, can be transformed into the corresponding red lines displayed in the diagram. The transformation of this description of the feasible region of a compressor unit into the quantities we consider, which are pressure and mass flow, will be part of the exercise session for today's block of videos. As elements in our network topology, we do not consider single compressor units, but compressor stations. These represent the combination of multiple compressor units that can be used in a combined fashion to perform the desired compression operation. To achieve a higher compression ratio, single units can be combined in series, while a parallel combination allows for a higher flow throughput. The different possibilities to combine the single units are stored as configurations of the compressor station. In addition to these, a compressor station also has a bypass with a valve. Therefore, it can act as an open or closed valve, as we have mentioned already before. In a typical gas network, the active elements are not evenly distributed throughout the network, but are collected in small areas to be able to realize complex control tasks in cooperation. These areas, consisting of multiple active elements, are called network stations. Network stations are often located at the intersection of major transport pipelines. Here, they may increase the gas pressure for the next pipeline section or allow for different ways to inject gas from one of the pipelines to the other one. Here you can see two examples of very complex network stations. They contain multiple compressor stations and regulators, as well as plenty of valves to be able to link the connected pipelines in different ways. However, not all of the theoretically possible mode combinations of the single elements in a network station are allowed. For example, it is not feasible to have an actively running compressor station surrounded by closed valves. Hence, each network station has a set of valid mode combinations of all contained active elements. These are called the operation modes of the network station. On the right-hand side, you can see an animation of different operation modes of an artificial network station. Here, the connected pipelines are linked in different ways, and the contained compressors work in series, in parallel, or are even assigned to different exits of the station. Okay, now you know how to theoretically operate a gas network. You should be able to write down a model for the single elements, build a toy example like the one you have seen before, and solve it with some self-created scenario by using an appropriate solver. However, this is not the goal we had in our project. We wanted to solve the problem of finding a control for a real-world network in a short amount of time, such that the result can be used to help the gas network operators in their daily work. Unfortunately, there are quite some differences between the theory and a gas network problem from the industry. The gas network existing in reality has grown over the last decades and has been extended multiple times to keep up with the changing transport requirements. Therefore, there are, in addition to the standard elements we introduced so far, a lot of unique network elements, or even network parts, that have a special purpose and may work completely different than all of the other network areas. For some of those elements, we can model their corresponding influence on the gas network operation by using the artificial resistor element. It can be used for all sorts of network equipment that serves a special purpose but is not relevant to the actual network operator. Since these elements cause some additional friction, we cannot simply ignore them, but use the resistor to induce a certain amount of friction in the direction of the flow. The formula, that is also displayed on the slide, is similar to the one we used for the friction in the pipelines. One example for these elements are metering stations that are used to measure the state in the network, for example the pressure. Also, gas coolers and heaters are modeled in the topology as resistors. The last two are necessary before and after compressors and regulators, since the gas temperature changes with the pressure, but should be kept at a similar level throughout the network. As a second category of special elements, we have those that can be sorted into one of the presented standard element categories, but nevertheless work differently than usual. One example for this is a piston compressor. The standard compressor unit type used in a network is a turbocompressor. It compresses gas using a centrifugal impeller and is also part of a typical jet engine. However, in one of the network stations of our project partner, there are still old piston compressors. They work similar to car engines and compress the gas by moving a piston up and down in a cylinder. Another example for a unique element is a compander, which is again only present in a single network station of our project partner. This is a compressor that uses a special type of drive, which draws its energy from regulating gas in a neighboring part of the network next to the compressor machine. Finally, there is an element called integral regulator module. This is an autonomously working control unit for a regulator that can be activated by the network operator, and whose control decisions have to be anticipated from our model. Besides the special network elements, you may also find whole parts of real-world networks that serve a particular purpose and have a unique set of rules attached to them. The following two are again examples from the network of our project partner. First, there is an area called the breathing bag. This is the name of a dead-end pipeline attached to the network, which is used for calibrating the behavior of new network elements. Therefore, this network area has an unforeseeable behavior that still influences the surrounding network parts. Then there is an area in one of the network stations that was introduced to us as the gatherer. It represents a part of the network station that should, in most of the cases, be operated at the same pressure level in order for the network station to work properly and as intended. In addition to the new models needed for the non-standard network elements, we also have to extend some of the already introduced element models. So far, we presented a description that represents an amount of detail usually used in scientific publications. However, we need to consider some additional aspects to cover the real-world element behavior. One example for this is the target value or set point-based control used for regulators and compressor stations. For these elements, the network operator cannot specify the point of operation directly, but can only indicate desired levels for the involved quantities, like for example a desired outgoing pressure level as well as the desired flow throughput. The compressor station then tries to achieve these levels based on an internal set of rules. When recommending actions to the network operator, we have to specify our solution using this rule-based system as well. Another detail of compressor stations is the fact that most of the power providing drives run by using gas directly from the network. Therefore, these compressor stations also represent a gas flow exit if they are active. However, since the gas used to power the compressors is only tracked in summary over the whole network, the single element consumption rates are not known. This complicates the setup of an appropriate model that includes the local gas volume changes due to the current compression levels. As a last point, the demands for the future are based on contracts that the network operator sells to transport customers. Some of these contracts include the possibility to interrupt the gas delivery, which the network operator can use in severe network situations. Therefore, changing the demands is another control option that exists in reality. Apart from the differences in the general setup of the network topology, there is another difference between theoretical and practical gas network control. The network changes over time. This has several reasons. First, single elements can be out of order and are therefore currently only partly or not at all functional. Then there are general maintenance operations, in which whole network areas may be shut down or only one of two parallel transport pipelines can be used. In both cases, the usual set of rules for these network elements or areas may not apply anymore, which then causes unexpected behavior of your model. From time to time, also expansions or reconstructions can happen, which may introduce new element types and change the current network structure. On top of that, our project partner has a mobile compressor, which they use for maintenance or network repair operations. If you want to find out more about this topic, you can have a look at the linked webpage. Because of this, a single compressor may appear somewhere in the network from time to time. All of these points makes a search for structural properties of the network, which you can then exploit in your solution routine, extremely challenging. Last but not least, the pure size of real-world networks is often a challenge on its own. In the small example we showed before, you could clearly observe and understand the physical consequences of the single control decisions. For the network of our project partner, even the practitioners sometimes have problems to understand the complex element interactions in the bigger network stations. Therefore, the search for a stable control for all of the single elements in the whole network that enables the safe transport of gas according to the given demands is a tremendous challenge. So what to do? Sadly, I cannot give a definite answer to this question. However, based on what we did in our project, I would like to give you some general advice on how to approach problems that represent real-world scenarios like the one on gas network control. As we have seen, a realistic problem description involves a lot of elements as well as a vast amount of technical details for each of these elements. Therefore, the approach of creating one single model, plugging it into a solver, and obtaining a solution in a reasonable amount of time is very likely not going to work. Otherwise, you would probably not have been asked to help. As a consequence, you have to find ways to simplify the problem or split it into multiple parts. Another property of realistic models is that the accuracy of the description for single elements can often be enhanced by increasing the size of the formulation. For example, by changing the granularity of the discretization of some continuous quantity, like the time. Therefore, we have a natural interest to answer the following two questions. What amount of detail is required? And are there certain decisions or features which are more important for the overall solution quality than others? These questions are typically non-trivial to answer. Since practitioners are usually not used to these types of questions, they may give you different answers for each person in the company you ask, or you just get some general feedback like, everything is important. So again, the question is, what to do now? When you start your project on a problem like ours and reached the state where you got a basic idea of it and understood how things work in general, we would recommend to first aim for a solution that is simple, small, and fast. What does this mean? The important thing is to get something running as early as possible in the project. The initial model should cover only a very basic description of your problem. Just use some common formulations from the literature or from a previous project if possible. If your problem contains some more complicated parts, which most likely will be the case, try to find some easy approximations for them for the start. If you have set up your model, run it on some small instance of the problem, which solves fast by using some black box solver. By doing this, you have a fast way to debug and adjust your initial implementation or compare different approaches. When choosing this initial instance, it is important to use some real-world data if possible, maybe a small and easy-to-solve subset of your problem. We, for example, created our first test set by using this lower left pipeline cutout of the network. By doing so, you already have an early check if your implementation can handle some of the real-world characteristics, which, as you have learned, can vary greatly from the theoretical models. In addition, also the data you get from your project partner is checked for errors, which in our experience should happen as early as possible in the project. For the examination of your results, we recommend obtaining or creating a good visualization tool. For example, you don't want to look at a long list of numbers when you try to find that element at that time at which the pressure jumped unexpectedly to the maximum value, even when only looking at a small test instance at the start. This visual representation of your solution can also be used to present the results to other people, for example the practitioners, to get some feedback on your current model. Based on this feedback, the model can now be improved to get closer to what is actually happening in reality. When asking the practitioners what problems they see in your current solution, you want to focus on two types of errors. The largest problems that your results currently have, and those errors that can be easily added to your solution approach and don't make the problem harder to solve from a mathematical point of view. Solving issues of the first type provides the biggest improvements in solution quality, while the second type cases are just low-hanging fruits you should collect. If the new features result in a significant performance loss, you need to update your current approach. Since we started with a rather low model accuracy, more simplifications are probably not possible. Hence, you should look for ways to split up the problem into multiple parts. We don't advise to start too early with some solver-specific performance tuning, like adding specialized heuristics or cutting plates to a MIP solver. If you still need to add new components to your model, and even your overall solution approach may change, the effort you invested to achieve the speedup would have been for nothing if these tunings can no longer be applied after the update. By repeating this general procedure, you are on your way to step-by-step create a functional tool for solving the original problem. This approach has various benefits. One major plus is that the question regarding the importance of single features or properties is often easier to answer for the practitioners. It is typically simpler to search for some unexpected behavior in specific examples than to describe the properties of some element in general. The most important missing features will be pointed out with the most urgency, or are detectable by comparing your solution with a given realization from reality and search for the biggest differences. By doing so, you sometimes also find new specifications that have been forgotten so far. Another advantage of this approach is that you only include those element properties that have an actual impact on realistic data. Certain special cases may exist in theory, but never happen in practice, so spending time on supporting these is often wasted. As one example from our project, the constraints regarding the gatherer have never been added to the model. Nevertheless, the corresponding network station works as expected even without these. Finally, the approach minimizes the dependencies between the different involved parties, which results in a larger amount of time for everybody to do their job. The mathematicians can start very fast with the first implementation based on the given literature or only a rough problem description. This gives them time to get a feeling for the problem and better understand its structure. On the other hand, the practitioners do not have to provide a complete problem description including all the different technical details and unique special cases right at the beginning, but also get some time to do some research and set this up. When you follow this procedure, you will encounter the issue of having no specified problem statement. This can be rather unintuitive for mathematicians, since typically the first thing you see of a problem is a complete problem statement. Here, the problem changes over time, and some of your first ideas to solve the problem may become unsuitable if they are not compatible with newly added features. However, you can make the argument that a complete problem description is in general hard to get, and may just not be available independent of the effort you may invest here. The second drawback is the quality of the early solutions. When you show results obtained from a simplified model to practitioners, they may be surprised that you didn't even manage to include features that they evaluate as trivially to add. You may have to spend quite some time to convince them that even largely inaccurate models can be a valuable part of the process of creating a working solution for a complex real-world problem. That's everything from me for now. In the next videos, my colleagues will introduce our solution approach to the problem, which was created using the method I just presented. Have fun watching these and see you in the exercise sessions. Bye bye.